Okay, this is the Tech Math 3 Pre-Calculus Combined class. We're in section 9-3, and we have some rules. And the first rule says, if I have the log of m times n, and it doesn't matter what the base is, that's the same as log of that base times m plus the log b n. No, definitely not. And the next rule says if I have the log base b of m divided by n, that I can rewrite that as the log base b of m minus the log base b of capital N. But n cannot be 0. What's the problem?
What's the base on the one on top?
B. B for base, yeah.
Okay.
Yeah, B for base. Yeah, I try to be original in most of my notation. My handwriting is always bad, but the notation just makes perfect sense.
Of course.
Yeah, of course. And then we have another rule, and which would require us, of course, to go to a different color. So the log to some base of m raised to the n is going to be n log that base m. So when I have an exponent, I can bring that exponent out in front and not lose any continuity. And as a corollary, the log some base m to the 1 over the nth root. We'll take the nth root of n. Get rid of this guy over here. And that could be a fractional root. I could have written it as fractional root. 1 over n log some base m. And the log of any base again of 1 is always going to be 0. So it doesn't matter, base 10, base e, base 5,000 million of 1 is still going to be 0. And if I have the log of some base 1 over m, then that's the same as minus log of that base, capital M. So those are my log rules. Two more. Log some base of the base raised to the x power is just going to be x. So the log function and the exponential functions are mirror image of each other. So if I take the log of some exponential in the same base that the log is basis of, then I get whatever the exponent is. Was that mealy mouth enough? Okay, good. And again, if I take a and I raise it to a log, well, we won't do that. We'll do something different. We'll go b raised to the log base b of x. We end up getting x back. So those two rules are again the mirror image of each other. If I take the log of the exponential, I get the x. If I make the log the exponent of the base, then I get the x back too. Isn't that cool? Totally cool. Yeah. Anyway, so too many rules. I know. That's just the way it is. So now we're going to go and do problem number 2. I have 8x squared y cubed z to the 4th, and I want the log base 3. And I'm supposed to write this in expansion form of sum differences and multiples of single logs. All right, so that's what I'm going to do. So I've got log base 3 of 8. No, I don't. I have I have 3 log base 3 of 2, because I recognize as 8 as 2 cubed. So this guy here is 2 cubed, so I'd break that out too. Plus 2 log base 3 of x plus 3 log base 3 of y minus 4 log base 3 of z, and I'm all done. So I'd taken something very simple looking and made it very complicated. And one foul swoop. Didn't take me any more than a half minute.
Can we go over that one more time?
Yes, we will. We'll do it with number 8, as a matter of fact. So, number 8. You're slowing down the YouTube video considerably by. Yeah, and I'm not going to go back in and cut and paste this section off. That's killing time. Oh well. So when things are multiplied together, when I have a log of things that are multiplied together, I can add the separate logs. Now why is that? Well, I have rules that said I could, right? Okay, so okay, I have rules that said I could. All right, so that's one thing. But does it make any sense? Let's see. I got log base 10 of 10 squared times 10 cubed divided by 10 to the 4th. Okay, so I got that. Okay. Gonna have to keep up, Ramundo. That was a. All right. So that's what I got that. All right. So I can say that that's log. That's 2 log base 10 of 10 plus 3 log base 10 of 10 minus 4 log base 10 of 10. Okay. Well, what's log base 10 of 10? 1. So that's 2 plus 3 minus 4, which is going to be a 1. Well, if I would have rewritten this, I could have had log base 10 of 10. What's the log base 10 of 10? 1. Okay. Does it make any more sense now, or is it just muddied the waters more? Yeah. But when things are multiplied together or divided inside a log thing, adding, well, let's put it this way. This is a calculator, okay? Prior to the calculator, how did we multiply?
Abacus.
Using a slide rule.
Oh, yeah.
Okay. We multiplied on a slide rule by adding distances on the slide rule, right? No, you don't remember because you never even had one.
Yeah.
Okay. If I make a ruler, I put a log scale on a ruler, and I add the logs, that's the same as multiplying. Okay, so back 30 years ago when we didn't have calculators, and we were 40 years ago, and we were using slide rules, which I did all through high school, all through college. I didn't get my first calculator until graduate school in '79, and I graduated from college in '72. So all through college we used slide rules to multiply and divide and take roots of things. We did it by adding and subtracting logs to multiply and divide. So that's all we're doing here. If you add logs, that's the same as multiplying. Okay, but you never used the slide rule, so you never had the pleasure of doing that. All right, back to number 8. Log base 5 4th root x y squared z. It is in my book number 8. What is your problem? What's the front of those problems?
Wasn't the last one number 8? The last one was number 8.
Yeah, I got number 8 right there.
No, that was the last one.
No, we never did number 8.
He was his help doing a problem.
Oh. Mundo, you're not keeping up. See, I put an 8 there, and then I didn't do number 8. I did an example to make it easy for you, and then I'm back here trying to do number 8, and all I get is lip. You know. Anyway, what was I doing? Anyway, so we're gonna rewrite the problem and say, well, this is 1/4 the log of x, y squared, z. And then we're going to say, well, that's going to be 1 minutes log base 5 log x plus 1/4 times 2 log base 5y plus 1/4 log base 5 of z. And then I go back and say, well, 1/4 of half is 1/2, so I put a 1/2 there. Boom. And final answer, equal sign, equal sign.
125. 1.5.
Okay, so we're done doing that. Now we're going to start doing the other way. So now we're going to do it the other way. Number
Go
22,
over there, Enrique? Sweet. Can I put it over there?
log, what's your problem? Never mind, I don't want to know.
I get a seat on the front.
Plus 1/2 log base 3 x plus 2 minus 3 log base 3 x minus 1. Okay, now all the logs are base 3. So that means we can put it inside one lousy log, which is what we're supposed to. Put a bracket down. Okay, so I've got an x plus 1 times the square root of x plus 2 divided by, because I got a negative sign, divided by x minus 1 cubed. I'm all done. I did it in one line. Okay, when I add logs, that's the same as multiplication. When I multiply a log, that's the same as taking a power. How long has it been that way? Oh, no. No, probably not. Since Newton? Yes, at least since Newton. Probably 300 or 400 years before Newton. You figure that the numbering system we use didn't get given to us until the North Africans gave it to us in about 800 AD. So before 800 AD, there was no such log thing going on. But it was something that Newton used. So that was a long time ago, right? Before Columbus. Well, not before Columbus, but before the Pilgrims. Okay, now we're going to do number 28. Number 28, log base 2, 2 to the 5th. I'm going to rewrite that as 5 log base 2 of 2. The log of in any base of the base is 1, so the answer is 5. And how far do I go? 37? All right, so I'm going to use 30. I'm going to do 36, and then we're done with the section. Number, you aren't, but I am. Log base 10 of 10 to the minus 1. Minus 1 log base 10 of 10 minus 1. In fact, I would have written down minus. I didn't have to do that last step. I could have just gone minus 1 there, because log of the log function means of some base. If it's that base raised to some power, it is that power. That's the whole definition there. Okay. So now we get to go backwards. 9-4, we get to go to common logs. So if I just write down log, and there's no number there for the base, then that implies base 10, which is the common log. So if I don't tell you what the base is, then it's base 10. Your calculator has a log key, LOG, that's base 10. Okay, that's all it is. It can't be anything else. Your calculator is always base 10. Okay, there's no, yes?
Was the answer to the last problem -1?
-1, yeah. Didn't I put down a -1?
So
Like twice? Yeah.
it's safe to
Yeah,
assume
negative.
anything that just says log. Is it just safe to assume that anything that says log is just log base 10?
Yes.
Okay.
If it says log, LOG, it's base 10. Period, the end. The only other one that that you could see that's as similar would be a ln, which is natural log. But that's not until section 5, and we're not even there yet for another 15 minutes or so. So we don't have to worry about that. Okay, so that's where we are. Now, it appears we have no new rules. So there's no new rules, so common logs act the same as regular logs. And we'll do number 4 first. And so we want the log of 14,000. And we want it to 4 significant digits. All right, so I take my calculator, and where's the stupid log button on this thing? All right, log 14,000, and I get 4.15. 4.1. No, I don't. I need 4 significant digits. 4.146. 4.146. Yes, that's. We take our calculator and we do it. Yeah.
Just round everything to 3 sig figs for most.
The problem in the book says show 4 significant digits.
Oh, okay.
So that's what I'm doing.
Okay.
Yeah. So if the problem said show 35,573 significant digits, then I'd be hosed. I couldn't do that. But if it only says to do 4, actually there is a way to get 33,495 significant digits if I wanted them.
Keep pushing it over.
But that's not until, I don't think that's until chapter 29, and we don't get to there, so. Yeah, well, there is a way. The Tech Math 3 guys will get to that point next semester. Remind me to do that. Find the log to 35,000 significant. All right. Where do you find the log on your calculator? You pay the extra $10 and buy a better calculator. All right, log 1. All right, 1. I'm guessing it's 0.
That's number 12?
Yeah, that's number 12. I'm guessing it's 0, but I'm gonna use my calculator anyway. Where's the log button? There, I found it. Log 1. It is. It's 0. Cool. So is that right? Long minus 0.1 significant digits. It says to give 4 significant digits, right? 0.000. Now, for the pre-calculus guys, there's nothing wrong with that answer. Perfectly okay, 0. For the Tech Math 3 guys, no. Significant digits are wrong, minus 0.1. All right. All right, now we got to go the other way. Whenever you go one way, you got to go the other way, right? What? Got a problem? No problem? Are you sure? I got a problem. All right, so 14. What am I doing in green? The log of n is 2.6191. And again, I want 3. I want 3 significant digits. All right, well, so where is my log n key anyway?
Where's my login?
No, I don't see it. All right. But one of the rules said if I take the base and I take the log in that base of some number, I get that number, right? Remember that rule? That was like a half hour ago. Yeah. So that means if I take this and raise it to the 10 log n, and I have 10 to the 2.619, I have the same thing. I can use, if two things are equal, if I have A is equal to B, then 10 to the A has to equal 10 to the B, right? So I got log n is equal to some number, then 10 raised to that exponent has to equal 10 raised to the other exponent, right? And 10 common log raised to the n is just n. So I got n equals 10 to the 2.6191. It's also called an anti-log, if you want to know that. Okay, so now I've got a key. I got a 10 to the to the X key sitting on my calculator. So I use it. I put in a 2.6191, and I write down 3 significant digits, 416. And I'm all done. Yes. Well, get it out of hexadecimal. Might work better. All right, so that's what we're going to do. So if we have something, log of some number is equal to some exponent, equal to some number, we're just going to use that as an exponent of 10, write down the answer, and move on. We'll do 24. Yeah, so I got log n equals minus 6.8163. So n is equal to 10 to the minus 6.8163. And again, I'm only looking for 3 lousy significant digits. And it looks like I have 1.53 times 10 to the minus 7. Is that what I have? All right.
So for all those you want to read this
Well, I don't care. You could write that as 0.000000. Is that enough? 1, 2, 3, 4, 5, 6, 1, 5, 3. You could do that. It just said 3 significant digits. It didn't say how. Yeah, yeah. If it said put in scientific notation and you gave it in floating point, then that'd be pretty hosed. But you know, and my calculator didn't put it in floating point anyway. It had to put it in engineering notation just for me. You know. But if you had a graphing calculator that's giving you 16 digits, then there's no reason it might give it to you. But it wouldn't matter one way or the other. Yeah. Where was I? Number 26. So I got the log of 984 divided by the log of 4. All right? There's nothing I can do with that except put it in my calculator as written. I can't. I'm not subtracting logs anymore, so I can't divide. I can't do any of those other things. So I'm going to have to go log 984 divided by log 4. Three significant digits, 4.97. Okay, so another calculator problem. I just have to put in my calculator, right? So I put in log 984 divided by log 4. Enter.
The thing is, like, you're really like starting well.
Okay, good enough?
The best thing to do is to
How far do I have to go? 53? Oh. Okay, we'll do 46 next. 48. We'll do 48 next. We have 10 to the minus 14 watts per centimeters squared, and we want to calculate how many decibels I have. Okay. And we find that the number of decibels I have is 10 log intensity divided by intensity naught. 10
Listen up, fellas, come on.
log 10 to the minus 14 watts per centimeter squared. And intensity naught is 10 to the minus 16th. 10 to the minus 16th watts per centimeter squared. Okay, so this is 10 log.
Your last statement over there.
I can't either.
It's 10 to the negative 16 watts. Negative 4.
10
That's the top. The bottom.
squared.
And then it's whiskey.
Decibels are unitless. Those units that you can't read go away, so don't worry about them. In fact, I just take my red pen and go through them. That way you can't even read them less. Yeah. So it doesn't matter. The log, base 10, common log of 10 squared is 2. 2 times 10 is 20. 20 dB. Okay? Good enough? Yes, it is. Now, in your circuit analysis class, intensity naught was 10 to the minus 12 watts per meter squared. 10 to the minus 12 watts per meter squared and 10 to the minus 16th watts per centimeter squared are the same number. So for the front row that's confused because I'm doing something in a different set of units, that's interesting, but for the rest of you it won't make any difference. All right, so any physics majors? Anybody in physics? Chemistry? Any chemistry guys? One? Okay, so we got to do a chemistry problem. All right, number 54. Oh, 54, that's not, oh, 46, number 46. Yeah, 46. The hydronium ion concentration. Hydronium ion concentration is 6.1 times 10 to the minus third. We want to calculate the pH.
Is that pH?
What's pH?
That weird letter.
If you're keeping up, you would know what that was. The hydronium ion concentration. 6.1. Okay, so pH is equal to minus the log of the hydronium ion concentration. Okay, so yeah, so pH is 1 minus log of 6.1 times 10 to the minus 3. And once you know the hydronium ion concentration, you then know the HO one, HO minus. What's that one called anyway? I forget. Anyway, not my job. Not a physics, not a chemistry major. Okay, so I'm going to go log of 6.1 double E minus 3, and I'm going to put a minus sign in front of it. So the pH is 2.2. How many significant digits am I supposed to have? It doesn't say. Well, I only have 2, so 2.2. pH is 2.2. Is that good or bad? You want to swim in it?
Yeah.
Probably not. Yeah, pretty bad.
It kills all the bacteria.
All right. Well, one more section to do. 6.5. 9-5. 9-5. Now we have to deal with natural logs, which is base E. Okay, so the first thing we have to know, anybody know what pi is? 1.3.14159256, isn't it not? Is it not? All right, so we'll claim that that's what it is anyway. Now, how do we remember that? Your 9th grade. Okay, so the way you remember that is Columbus sailed the ocean blue in 1492. Okay, Now, what happened in 15? I think it's 65 though. Where's my pi
It is
button?
65. The 5 and 60 switching around.
Yeah, it is 65. Yeah, I know that because 65 didn't rhyme. 56, 65. There, that's better. Okay, so the issue is what happened in 1565? Not in 1565. Neither a man is still alive that remembers the voyage of Magellan, right? So Magellan supernavigated the Earth. So you're taking your SAT exam. They allow you to have a calculator, and they want you to know when did Magellan, circumnavigate the Earth. You want to put down he didn't. He died in the Philippines, right? Which he did. He never made it. His boat made it, but he didn't. You want to put that down, but that's not a choice. It's multiple choice, and you have to come up with a date. So you take your calculator, hit the pi key, and 1565, Magellan circumnavigated the globe.
That's it.
Now, all right, so we got that all straight now? Now, this E guy, which is the base of the natural logarithms, okay? So if I'm radioactive material and I'm decaying at a rate of E. If I'm your money in a bank account of getting interest, I'm gaining interest at the rate of E. If I'm a plant growing in the garden and I'm multiplying and I'm getting bigger, I'm growing at a rate of E. This thing is all over the place, you know. And so you go back to Genesis. It doesn't say God created E, but it certainly did bring a lot of people to pause in this 15th, 16th, 17th century when they're finding everything in physics has to do with this E, the natural base of the natural logs, and E is a transcendental number, which means it's a decimal number that never starts repeating. It's just like pi, goes on forever and ever. All right, well, anyway, 2.71828. Now, how do I remember that? Now, was pi known to the Greeks, ancient Greeks, 500 years before Christ? Yes. Did they know it as 3.14159268 and therefore knew Columbus was going to sail the ocean blue in 1492? Did they know that? No. Why not? Because we didn't have a decimal numbering system yet.
Yeah.
Right. So their idea of pi was some number about 3. It wasn't some repeating number that never repeated as a decimal. Went on forever and ever. Okay, same thing here. Now, after a thorough search, I took at least 45 minutes to search every single book, history book I had in the house to find out what happened in 1828 that was so important it had to be repeated twice in E. And guess what I found? That's it. It took me 45 minutes to find it. How could it be nothing? If it was nothing, it would have taken days to find nothing, right? It only took 45 minutes. Right. So, and it happened in the United States, and it happened in New York City, and it happened in Boston in 1820. No, it didn't have to do with taxation of beer. It had to do with the first public high school. So prior to 1828, if you went to high school, so that'd be anything past probably 7th grade, really, it would have been a private high school you were going to, and a very small percentage of the population did that. In 1828, the first public high schools opened up in both New York City and Boston. That changed the entire nature of our society. Can you, if that wouldn't have happened, can you imagine that we never had public high schools ever? You went to 8th grade and that was it. Well, your great-great-grandfathers and grandmothers, that's all they did. The whole country worked just fine. You know, we still had cars. We still invented cars. We still invented electricity. We still did other things, you know. And the elite of society went on to high school and maybe went on to college. Your physicians probably never went to college. You know, you just said they're a physician and sewed you up when you got shot by a gun or something, you know. But the whole nature of the world. Now, in Europe at the time, what's going on? Any idea? The girls aren't going to high school. That's not going on, right? What's going on? The boys are going to high school. To learn what? That's right. So they went to high school to be better soldiers. They went to academies and gymnasiums to be taught to be soldiers. And that wasn't broken until after World War II. You know, the whole reason to go to high school in Europe was to be a good soldier when you got out. You learned how to sharpen your knife, and you learned how to shoot your gun, and you learned how to march. And that's what caused the Prussian War, World War I, World War II. If you're training your whole population to go to war constantly, and you never go to war, you know, that's a waste of money, right? Stupidity up the wazoo, but you know, that's the way they're looking at it. And, you know, we have 3, 4, 5. We have 5 military academies where we train people to be Navy guys and Air Force guys and Army guys, but we don't train the whole population for war. We don't do that anymore. Anyway, so 1828, very important time. All right, back to, so now my calculator had 10 to the x on it, so I can do an anti-log. It has e to the x, so I can do an anti-common log. It has a log for common log. It has an ln for natural log. All the rules that apply the same. So instead of saying log base e, I say natural log ln. Okay, so that's so I save some ink. All right, now something clever is happening here. Let's say that I have log base b of x. Let's say that I have that. So I'm going to have log base 10 squared. It's going to be 2, right? Well, if I have log base b of x, that's the same as saying common log of x divided by common log of b. Okay? In my example down here, I would have common log of 10 squared divided by common log of 10. That would be 2 over 1, which would be a 2. It's also the same as the natural log of x over the natural log of b. Okay, so if I take the natural log of 100 and I divide it by the natural log of 10, I should get a 2. Natural log of 100 divided by natural log of 10, I get a 2. Okay, so this is a very interesting phenomenon in logs. I'm not sure why from a numerical answer. I'm sure that I knew back when I take my numeric analysis class back when I was 19 years old that I knew why, but I don't know why now. But the log of some unknown base of some number is the same as the log of that number divided by the log of whatever common log, which is the same as the natural log divided by the natural log. Very interesting. Another one of those things that you scratch your head about and say, who made this guy up? Now, in the physical world of reality, there is a physical world of reality out there, right? 300 years ago, the scientific community had this great big set of things that were known to be true. Okay? They saved that subset of things that were elegant. Okay? And they put them over here, and about 100 years ago they called that physics, and they started teaching that to you. The stuff that wasn't elegant, they threw away as being irrelevant. It wasn't elegant. Okay? So you look at things like the force of gravity, G, mass 1, mass 2 over radius squared. You look at the forces due to two charges being next to each other. K, Q1, Q2, distance squared. Elegant. They're different by a constant. This constant's 10 to the 9th. This guy, I think, is like 10 to the minus 12th. Difference by a constant, but it's the two masses multiplied together, the two charges multiplied together, divided by the distance squared. Makes it an elegant theory. Newton came up with this one. No, he didn't. Newton came up with that one. How do you spell Newton? Yeah. And Coulomb, C-O-U-L-B-U-M-B-O-M-B. Oh, that's misspelled too. S-P, probably S-P on this one too. Anyway, so that's just the way it is. They did that. Okay, they also did some other things to you that you probably are less aware of. So, when the King James Version of the Bible was made, that was a long time ago. That's about the time Enrique was born. When was that, 1610 or so? There was no theory of, there's no evolution. Evolution doesn't come for 200 years. In the first chapter of your King James Version of the Bible, did God create plants? No. He called them forth. Now, as a creator God, does it matter if I call them forth or if I create them? Probably not. If I was God, it probably didn't matter, right? I could do either one. Wouldn't matter. Right? But he called them forth. Well, evolution now occurs, and there's a big battle between the religious guys and the scientific community. So read your Revised Standard Version of the Bible, translation that happened after evolution came out. God created the plants. God created the animals. He didn't call them forth anymore. He created them. Did the original text change? No. Some scientific theory got it right. Physics people did the exact same thing. Second law of thermodynamics, things go from order to disorder. Order to disorder. Okay? Prior to evolution, it was perfectly okay. Things are that you have an ordered state, they're going to a disordered state. No problem. Evolution happens, and now we got a problem in the physics community. Are we going to tell the biology babes that they can't have evolution because it's impossible? Physics doesn't support you? No, we can't do that. So we add to the second law, in a closed system, you go from order to disorder. And the Earth is not a closed system, therefore it doesn't violate evolution. Right? Wait a minute. But where is a closed system? It doesn't exist anywhere now. So why have the second law at all if it doesn't apply to anything? Because it can't apply. And so you're there, and it's just one of those things. So instead of the physicists standing up to the biology people and telling them wait a minute, guys, there's something wrong with your theory. It can't be true because physics is true. They went in and changed the theory a little bit so that they wouldn't have to get into the argument. Yeah, bunch of hosers anyway. Anyway, back to what we're doing. 9-5. Obviously, there's not much here except problems to do. Up to 65. Okay. So we're going to go number 18. E to the 5/8. All right. Well, you're just going to put it on a calculator anyway, right? So E raised to the 5 divided by 8. 1.87? 1.87. Let's just hope questions like that are all over all the chapter tests and the quizzes and things. And that'd be really great, wouldn't it? We'll do, yeah, even Enrique could pass a test like that. Number 26. That's all right, he'll get even later. Natural log 0.705. Now, if it's the natural log of 1, it's going to be 0. If it's the natural log of something bigger than 1, it's going to be bigger than 0. If it's the natural log of something less than 1, it's going to be negative, right? So if you remember the log curve looks like this, passes through 0 at 1, asymptotic to the y-axis, right? So this had better be equal to some negative number, and if I get some positive number, then I know I fat finger in the key. 0.705, boom, natural log, minus 0.3, I'd go 50. Nah, yeah, I'd probably round it up 0.50. Do I have to put a bar above that to show 3 significant digits? No, no, I don't. It's significant. That third digit is significant as written. Is this guy a significant digit as written? No. So this guy's only 3 significant digits as written. Okay. All right, so we're going to do 34 next. Natural log x is minus 3.77. 3 significant digits. Okay, we're going to do the same thing we did in the last section. We're going to raise these as powers of e. E raised to the natural log of x is just x. So x is equal to e to the minus 3.77. Why didn't you just ask for that, author? I could have done that already when I had to explain squat. E minus 3.77, close parentheses, 0.0231. Yeah? Good enough? Okay. Seems reasonable. All right, number 42. A public high school in a city has an enrollment. So I got some enrollment. 1,400. Assuming a decline in enrollment of 4.5%. What will be the enrollment in 5 years? 5 years. Okay. So, on page 321, we find that some y is a e to the rn. Okay. So my enrollment at some time t is going to be my enrollment naught e to the minus 0.045 t. Okay, so that's how I interpret that. And then I say, well, Or is it? Yeah, I guess so. So enrollment after 5 years is 14300 e to the minus 0.045 times 5. 14300. At any time, you can just put this in your calculator. Minus 0.225. All right. 14022 times e to the minus 0.225. Boom, close parentheses. 11,339. And then I have to ask myself, how many significant digits do you think we have? We probably only have 3, right?
How can you do that?
11,300.
How can you do that?
Yeah. Good enough? 48. In every single DC circuit in the entire world, I is going to be equal to E over R 1 minus E to the minus RT over L, where I is in currents, E is in volts, R is in resistance, T is in time, Henry or inductance is in Henry. So this is a circuit where I have a lousy resistor and one inductor. That's what I got. And then I got some switch that I'm going to close. Right.
What's the symbol next to leash?
This guy? That guy? So this guy's the resistor, this guy's the inductor. All right, so the question is, how long does it take? Well, the wrong one. Find I at 12 milliseconds. Okay, so that's what we're going to do. So I at 12 milliseconds equals E, which is 12 volts, divided by R, 90 ohms, 1 minus E to the minus R, which is 90 ohms, T, which is 12 milliseconds, divided by L, which is 8.50 Henry. Okay, now, how big is an inductor that's 8 Henry? Okay, is it as big as my little finger? As big as my thumb? As big as the desk? Yeah, big as the desk, right. This is a really huge thing. I mean, normally you have millihenry things that are the size of my finger. So if I have a millihenry thing the size of my little finger, something that's 8 Henry has to be 1,000 times bigger. So that's gonna be pretty big.
That's a big one.
I could name names, but I wouldn't want to embarrass anybody. So as big as me. How's that? Is that good? Yeah, that big.
Chicken.
All right. So now we have to do the math. Now, before we do the math, we're going to do something else. This circuit has a time constant, R over L, right? 90 over 8.5. 90 divided by 8.5. 10.6. 10.6 seconds. It's going to take 5 time constants for the inductor to fully charge. So that's close to a minute. And we're looking at the current at time 12 microseconds. Wow, why would we want to do that for? All right, so it's going to be pretty close to maximum is what it's going to be. In fact, we could probably just write it down as being maximum and be okay. All right, why don't we do that? Why don't we just guess that the current at 12 microseconds is going to be, yeah, going to be small. Because see, what's happening is that the inductor, the voltage across the inductor is L di dt. And so it's going to be a lot of it's going to be a lot of current. The change in current. So when the change in current isn't there, it's going to be max. So this is going to be pretty small. Okay. Where was I? 12. Anybody know what 12 divided by 90 is? 12 divided by 90. Nothing important. Okay, so 12 divided by 90, 1 minus e to the minus. 90 times 0.012 divided by 8.5. Boom. 0.127. All right. Okay, so I got 12 divided by 90 times parentheses 1 minus e to the minus 0.127, close parentheses again, hit my enter button, and what do I have? 15.9. 15.9 milliamps. Is that enough to kill you?
Yes.
Yes, it is. That's if I had the right voltage across that, I could kill you with that. Okay, good enough? It is 222, and the class is supposed to go to 225, but it's a Friday, so we can leave early, right? Yeah, so we'll, yeah. Only if you want a grade in the grade book. If you're satisfied with a 0 in the grade book for the first quiz, then put it in your book and don't bother to turn it in. Yeah. Thank you. Thank you.
Here's Raimundo.